Hi, good morning. Today we are going through some problems which can be addressed using either permutations or combinations. So we start with a simple counting problem. So question one: in how many ways the symbols A, B, C, D, E, 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 E be arranged so that no E is adjacent to another E? So here we have one, two, three, four, four different different symbols, out of which four symbols are A, B, C, and D, and the symbol E is repeated five times. And we are looking for the arrangements in which no is adjacent to one another. So let us consider the different symbols like A, B, C, D, E first. A, B, C, and D. So these four symbols can be arranged in 4 ways. Now we can insert the remaining letters or symbols, that is five identical symbols, so that they are not adjacent to each other in between these four letters, and can place at the beginning and end of the uh, symbols. So we can place this 5 is at any of these 1, 2, 3, 4, and 5 positions. Since there are exactly 5 positions and exactly 5 symbols, or exactly 5 symbol E, then that can be done in only one ways, that is that can be done in 5C 5 ways. 5C 5 is equal to 1, and therefore this can be done in only one way. So the total number of arrangements is 4 factorial into 1, which is equal to 4 factorial. Now the second one is something more tricky. Prove that n factorial divided by 2 raised dn is an integer. So for that, let's consider. So we are going to prove it using the method of combinations. So we consider the symbols are x1, x1, x2, x2, x3, x3, x4, x4, etc. Some xk, xk, in such a way that um, 2k is equal to n. So we have n symbols, and so what we have is, here we have n symbols, and out of which um, two symbols are of type x1, two symbols are of type x2, two symbols are of type x3, and so on. So the total number of possible arrangements is given by n factorial divided by, um, since the symbol x1 repeats 2 times, 2 factorial, since x2 repeats 2 times, 2 factorial, into x3 remains 2 times, 2 factorial, into etc. Since xk remains repeats 2 times, it is divided by 2 factorial, which is equal to n factorial divided by 2 into 2 into etc. 2 k times, and that's equal to n factorial divided by um, 2 to the power k. And since this is the number of arrangements which we can have using these 2k symbols, that is always an integer. So this is an integer. So number of arrangements cannot be a fraction. So this n factorial divided by 2 raised to k is an integer. So this is a method of proof. It is based on the techniques of combinatorics. So that is our second question. Now uh, determine the coefficient of xy z square. So it is xy z square in the expansion of x plus y plus z all raised to 4. So we can expand this x plus y plus z the all raised to 4 using multinomial expansion and identify the coefficient of x plus y plus z the whole square. That is possible. But the multinomial theorem states that the coefficient of x raised say x raised n1, y raised n2, z raised n3 in the expansion is given by n factorial divided by n1 factorial into n2 factorial into n3 factorial, and this n1 and n2 and n3 up in a way that n1 plus n2 plus n3 is equal to n. So we can use this particular result to find out the coefficient of x, y, z square in the expansion. So here it is x raised to 1, y raised to 1, z raised to 2, and the coefficient of x, y, z square is equal to, here we have n is equal to 4, so this 4 factorial divided by 1 factorial into 1 factorial into 2 factorial, which is 4 factorial divided by 2 factorial, which is 1 into 2 into 3 into 4 divided by 1 into 2, which is 3 into 4 is equal to 12. And in such a way, in a similar way, we can find the coefficient of x, y, z square in the expansion of w plus x plus y plus z the all raised to 4. And here the term is written as w raised to 0, x raised to 1, y to the power 1, z raised to 2. And the required coefficient is n factorial divided by, or 4 factorial divided by 0 factorial into 1 factorial into 1 factorial into 2 factorial, which is equal to 4 factorial divided by 2 factorial, since 0 factorial is equal to 1 and 1 factorial is equal to 1, and that is same as 12. Now so another one, how many triangles are determined by the vertices of a regular polygon of sides n? So if we consider a regular polygon of n sides, so let's just simply consider a polygon, regular polygon with 6 sides. So illustrating, not the proof. V1, V2, V3, V4, V5, and V6 are the vertices. Now we are looking for how many triangles are given by the vertices of a regular polygon of sides n. So here, if we join any three of the if you choose any three of the vertices, that will give rise to a triangle, and the order of the triangle is immaterial. So any selection of three distinct vertices from the uh, n vertices gives a triangle. So there can be n c 3 triangles. So that's the number of triangles possible uh, in a regular polygon with n vertices. Now, what happens if we are looking for the number of triangles for which uh, the sides of polygon is not a side of the triangle. So let us consider this case, and in which uh, if you look at number of triangles for which this particular side, say S1 is a side, then naturally the vertices V1 and V2 are automatically selected. And if you choose the third vertex, so here two vertices are already chosen, and what happens, we have to choose the other vertex. So if the other vertex is V5, then the triangle formed contains two edges of the polygon. So we cannot choose V5. And in a similar way, we cannot choose V3, because if we choose V3, then uh, V1, V2 and V2, V3 are sides of the polygon, and that is not working. So there's one possible selection is say V4, and if we choose V4, then this is the triangle, and this triangle contains only one side of the polygon. So how many such triangles are possible? So if we choose a particular side, that side can be chosen in n different ways. So a side can choose in n ways. Then whenever we fix a particular side, the n vertices of that particular side uh, cannot choose any further, and the vertices which are adjacent to or near to v1 and v2, or the chosen edge, cannot be chosen in our next step. So the next vertex can choose the third vertex, can choose from n minus 4 vertices, n minus 4 vertices, and we are looking only for one vertex, so that can be done in n minus 4, not plus, it is n minus 4. N minus 4 3 one ways, that is equal to n minus 4. So the total number of triangles out of this NC3 triangles with one common side with the polygon is n minus 4. So we can first we choose a side, then the third vertex is chosen from n minus 4 vertices, and that can be done in n minus 4 ways. So the total number of vertices, sorry, total number of triangles is n minus 4 into, this is a case of a particular side, then there are n different sides, so n minus 4 into n. So that's the number of triangles which have one side common with the given polygon. And if you are looking for number of triangles with two sides common to the given triangle, say if you choose two vertices, two sides, say S1 and S2, then there is no choice to be made. This third side of the triangle can be obtained by joining the non-adjacent vertices of our selection. So, so this is the case, some case. So if you choose these two sides, then there is only one possibility: join them. So how can we choose this three vertices? And if you list down the vertices v1, v2, v3, v4, etc., up to vn minus 1 or vn minus 2, vn minus 1, vn, we or arrange all the vertices in an order, then first we can choose these three, v1, v2, v3. That's a method of selection. Then V2, V3, V4 is another selection. V3, V4, V5 is another selection, and so on. V3, Vn minus 1, Vn is a selection. Then Vn minus 1, Vn, V1 is another selection. Vn, V1, V2 is a selection. Then the next possible selections are repetitions of the given edges in order. And these selections can be done in n different ways. So in total, we can have n triangles with the two sides common with the given polygon. And obviously we don't have three sides common with the given polygon. That's possible only when we have a triangle. If you have a triangle, then we can have uh, a triangle with three sides common to it. And for all other regular polygons, uh, we cannot have a triangle which is defined by the three sides of the polygon. So what we have is, in total we can have NC3 triangles, out of which n into n minus 4 is a triangle which have one edge common to the given polygon, and there are n different triangles which have two sides common with the given polygon. And if you are looking for the triangles with no sides common to the polygon is given by nc3 minus n into n minus 4 minus n. So that's the number of triangles with no sides common to the given triangle, that is nc3 minus n into n minus 4. And here actually what we count is the number of triangles which have no sides common to the given polygon, that is something like this. This particular triangle has no sides common to the polygon. So we are counting the number of triangles like this. Or in this particular case, we can have another triangle like this. So in the case of 6 vertices, we can have 6c3 minus 6 into 6 into 6 minus 4, that is 2. This number of triangles, and this is equal to this minus 6 minus 12. Then 63 is 6 factorial divided by 6 factorial divided by 3 factorial into 6 minus 3, that is 3 factorial. And this number is equal to is 6 into 5 into 4 divided by 1 into 2 into 3 minus 6 minus 12, that is minus 18. And this is equal to can cancel this 2, that is 2, so 2 into 2 4, 4 into 5 20, so it is 20 minus 18, that means equal to 2. So we can have only two triangles which have no common sides with the triangle with polygon with 6 sides, and thus that two triangles are given here. And we cannot have any other triangles which do not share a side with the given polygon. So that is uh, an interesting problem. And now this different type. If n is a positive integer, then prove that cn2 plus cn minus 1 2 is a perfect square. So it seems to be a tricky one, but it's not that much tricky. It is a straightforward one actually. So we just substitute the values of C and C2 for C and C2 and Cn minus 1 2, that is n factorial divided by 2 factorial into n minus 2 factorial plus n minus 1 factorial divided by 2 factorial into n minus 1 minus 2 factorial. And if you simplify it, it becomes 2 factorial is 2, and the numerator, when we cancel n minus 2 factorial from n factorial, what we have is n into n minus 1 divided by 2, then plus here we have n minus 1 factorial, and here it is n minus 3 factorial, so it is n minus 1 into n minus 2, and the remaining terms is cancelled with n minus 3 factorial divided by 2, and that is on simplification we have n square minus n divided by 2, that 2 can be taken as a common factor, then here it is plus n minus 1 into n minus 2 is n square minus 3n plus 2, and that is equal to, we can combine this 2n squared, so it is 2n square minus n minus 3n, that is minus 4n, then plus 2 divided by 2, and this thing is equal to n square. If we take a 2 as a common factor and cancel with 2 in the denominator, we have n square minus 2n plus 1, and this is equal to n minus 1 the whole square, and by binomial theorem we have n minus 1 the whole square is equal to n square plus 2 into n into 1 plus sorry, it is alternatively positive and negative, so it is negative, then positive 1 square is equal to n square minus 2n plus 1. So this is an application of our binomial theorem. Anyhow, n is an integer which is greater than 1 and is positive. So since n is an integer which is greater than 1, n minus 1 is also an integer and its square is also an integer, and the value of nc2 plus cn minus 1 2 is perfect square. So the square root is n minus 1 and it is positive. N minus 1 is an integer which takes at least a value of 1. Since n is greater than 1, n minus 1 is greater than or equal to 1. So it is perfect square. So that's a few problems which is solved using permutations and combinations, and we can have more problems related to the fundamentals of counting in our next class.